Good evening. Thank you for coming to this workshop, Introduction to Deep Learning using R. Before we start, I hope you have received the email regarding the workshop materials on this website. So that's academy.isdsa.org. If you didn't see the email, make sure you will check your spam folder. And if you still didn't see the email, please let us know so that we can resend the information regarding the website to you. And on this website, you can find all the information related to the workshop. Once you log in using the login information you received, you can click on this link, Deep Learning using R. It will take you to this web page. On this web page, you can find the notes and slides on this workshop. For example, if you click on the HTML slides, it will give you all the information regarding this workshop. And certainly you can also download the PDF file if you want to print it out. We also have the markdown file. This is the markdown file I used for doing all the analysis in this workshop. If you are using RStudio, you can download this file and open it in your RStudio. Here, I open the file in RStudio on my computer. As you know, using RStudio, you can run the data analysis directly within R. So that can be convenient for you when you follow with my teaching here. Okay. I'll give you maybe like a couple minutes so that you can download the files here. In addition to the slides, you can also download the data set. There are 3 data sets here. I'm going to use them for illustration for the code. Okay. Once you download the files, you can open either the HTML slides or you can open the PDF slides. You are also encouraged to open the R Markdown file in RStudio so that you can run the analysis along this workshop. In this workshop, I will first present a typical psychological data set. I will use this data set to illustrate the whole process or the whole methods for deep learning. And then I will show you how to build a neural network model for the analysis of text data. After that, I will show you how to use a convolutional neural network for processing image data. Finally, I will reanalyze the text data using a recurrent neural network model. Let's first look at the data set. The first data set I'm going to use is called active data set. Active represents advanced cognitive training for independent and vital elderly. It is a multi-set randomized controlled trial. It was conducted in 6 different sets. Those sets include the University Alabama, and this center in Boston, Indiana University, and several other universities. The primary aim of the trial was to test the effects of 3 different cognitive training interventions. Those interventions were previously found to be successful in improving elderly performance on basic measures of cognition in the laboratory settings. For example, they were found to improve their cognitive demanding daily activities. The trainings include initial training, and then it was followed by boost trainings. There are 3 different cognitive interventions or cognitive trainings. They focus on memory training, executive reasoning training, and speed of processing training. And there's another group, it's called the control group. And in this control group, nobody received the training. The participants in this study were assessed at the baseline. So that's before the training. And then immediately after training. And they were also followed annually after the post-training assessment. In total, more than 2,800 adults were enrolled in the study, and 2,802 participants were included in the analysis sample. This sample includes 26% of African American participants. In this workshop, we only use a subset of the active data for the purpose of illustration. In total, there are 2,290 participants. We have data on 5 different variables in the subsets of data. The first variable is called intergroup. So that basically represents the 4 training groups. And for this variable, it is a categorical variable. 1 means memory training group, 2 means reasoning training group, 3 means the speed training group, and 4 means the control group. Another variable is age. The third variable is gender, with 0 being male participants, 1 means female participants. We also have 2 test scores. HVRTT is the verbal test score before training. HVRTT2 is the verbal test score after training. So therefore, in total, we have 5 variables in this data set. Now let's first get the data into R. We can take a closer look at the data set. To read the data into R, I'm going to use there was some issue with my PDF file, so I'm going to close it and reopen it. Not sure what happened here. Let's see if it works this time. So to read the data into R, I'm going to use the read.csv function. The name of the data file is called active.dl.csv. So that's the data file you have downloaded from the website. And if you put the markdown file in a different folder from your dataset, and then you may want to change the working directory. As we know in R, we can use the function setwd to change the working directory. And if you have downloaded the markdown file, and then you can open the markdown file in R. And within that, you can read the data into R. For example, to use Command Enter on Mac, I can read the data into R. And to take a look at the content of the data set, here the name of the data set is called active. To look at the content of the data set, I can use the function str structure function. And str active gives me the basic information of the data set. For example, it tells there are 2,290 observations with 5 different variables. Okay. And the first variable is this one, the grouping variable, and then age, gender, verbal test score before training, and the verbal test score after training. For the convenience of demonstration later on, I'm going to rename the variables in the data set. So I use names function to rename the variables in my data set. Now I create several variables called x1, x2, x3, and x4, as well as y. So obviously, I'm going to use y as my outcome variable. So x1 previously is the grouping variable, x2 previously is the age variable, x3 is gender, x4 is the training score before training. Certainly, in a lot of data analysis, you may not want to do this because once I renamed the variable names in this way, those names are far less meaningful. And if you don't know the data very well, you may not know what's the meaning of the variables here. But here I only have 4 predictors, so it will be easy for me to remember them. And also later on, I don't need to type the long variable names in my data analysis. In general, in practice, you don't want to do this, okay? In our data set, the grouping variable is a categorical variable. And it's also a nominal categorical variable. To use this variable in any data analysis, typically we need to recode the variable. And here I recoded the variable use dummy coding. So basically for dummy coding for any categorical variable with k different categories, I can use k-1 dummy variables to recode the information in that categorical variable. A simple way to recode the data is to use the model matrix function. The model matrix function can be used to output the design matrix for a model, for example, for the regression model. Here I use the formulas. You can use the format x and tell there regress on y, y regress on x. You can use the formula like this. Here, since I'm going to recode the predictor, I don't have an outcome variable. So therefore, I left this part empty. So it's directly tethered on the factor of x1. The reason I use the factor function is x is a numerical variable originally coded in my data set. Okay. I need that there are no, this is not a numerical variable. Okay, it represents different categories of a categorical variable. So therefore, I use the factor function to do that. And certainly, I'm using the data set active. Okay. And when you use this, it will give you the design matrix. And for the design matrix, the first columns are the intercept. So it's always ones. And then the rest will be 0, 1, 1, 0, 0, 0, 1, 0, 0, 0, 1, and so on. Because I'm only interested in the dummy coded variables, which means I'm only interested in those variables. So therefore, I removed the first column here to keep this part of information only. So that's what I'm doing here. Okay, I use like a bracket -1. -1 means remove the first column here. Okay, and once I have the dummy coded variables for x1, then I combine it with the rest of my data set. Okay, I remember in my data set originally I have x1, x2, x3, and x4, and y. Now I want to combine them. So this is the information is the first predictor x1. And then the rest of the data set is here. I use active -1. Again, this would remove x1 in my original data set. Remember, in my original data set, I have x1 here. So using -1, I would remove this column in my data set. Now, if you look at my new data set again, I give the name active.new. Okay. And this new data set now has 7 variables. When there are 7 variables, we still have x2, x3, x4, and y. So that's 4 variables. But now we have 3 dummy coded variables, x1 and line 1, x1 and line 2, and x1 and line 3. For all these 3 variables, they only take a value 0 and 1. Okay. So here is exactly how we have recoded the first categorical variable. And in this categorical variable origin, that's x1. Right? So x1 has 4 categories, 1, 2, 3, and 4. And now if x1 and line 1 equal to 0, x1, 2 equal to 0, and x1, 3 equal to 0. So that represents the first category. Remember, the first category is a memory training group. And on the other hand, if x1 equal to 0, x2 equal to 0, and x3 equal to 1, then it represents the fourth group. The fourth group is a control group. Similarly, we coded the I think this is the memory training group, and this is the processing speed training group, and this is the reasoning group. Okay. Many times in data analysis, we can do standardization. Standardizing the predictors as well as the outcome sometimes can help an algorithm to converge or perform much better than the use of the original data. And because of that, here I'm going to standardize my predictors and my outcome to have mean 0 and variance 1. Since x11, x12, x13, as well as whereas the general variable are also already categorical variable or binary variable, we don't really need to rescale them. So therefore, I only focus on 3 variables here. One is age, another is verbal test score before training, and verbal test score after training. The function scale would standardize the data to have a mean 0 and variance 1. So these are the data of the standardization. I now further divide the data into 2 sets. One is the training set, another is testing set. And for the training set, I'm going to use that data to fit the model. For the test data set, I'm going to use it to evaluate the performance of my model. To select the subsets of data, I'm going to use their index. Okay. Remember, originally we have 1, 2, 3. In total, more than 2,000 participants, right? If I can find the index of those values to use, and then I can select the subsets of data. Okay. I want to randomly divide the data set into 2 parts, training data and testing data. To do that, I randomly select the participants of the original randomly select the index of the participants from my original data. Okay. So here I randomly select 2,000 participants or 2,000 indexes from a total of 2,290 indexes. To make sure each time I will select the same participants, I use set.seed to set my random number generation algorithm seed. And if you use the same seed, then each time you will get the same participants. If you don't do this, then each time you will have different data. So your data analysis results may change. So this is the index for the participants in my training data. And the rest of the participants will go to my testing data. So I use negative training dot index. So this basically remove any value in this training index. So that's the data I'm going to use to demonstrate the neural network models. With this data set, some questions can be answered. For example, one question could be, can we predict the verbal test score at time 2? That is the test score after training. Using the verbal test score at time 1, basically before training. Certain things we have other variables, we also want to know whether other variables can also be used to predict the verbal test score at time 2. So we will include all the other variables in the data set, including age, gender, and the training group variable. In the past, you may have learned ways to do this kind of prediction. For example, we know we can use regression analysis to do the prediction for an outcome variable from a group of predictors. So in this workshop, I will first show you how to do this regression analysis to predict the outcome variable. And after that, I will show you how to use neural network models to do the same prediction. As I just mentioned, to predict the verb test score after training, we can use the verb test score before training, age, gender, and training group through a regression model. So for example, this is the regression model using formula. Y is our outcome variable. In this case, it is the verb test score after training. And then we have a set of predictors. Firstly, we have training group variable, x11, x12, and x13. So those three variables are actually represent one single training grouping variable, okay? And then we have x2. I missed the plus sign here, plus beta 2 times x2. X2 is the age here, and plus beta 3 times x3. X3 is gender, as we know, and then plus beta 4 times x4. X4 is the verb test score before training. So this would be our regression model. Certainly we may have some error here. And this is a population model. Once we specify the regression model, we should estimate those coefficients using our data. Okay. I didn't mention beta 0 is certainly the intercept term in regression analysis. Okay. Conducting regression analysis in R is very easy and straightforward. In R, we have a function called LM, so it's called a linear model function. And in this function, we can specify our outcome and predictors, and then we can estimate our model. To specify the model, we can use a formula here. So notice that here I use y, tilde, and period. This means the outcome variable is y. Period means I'm going to use all the other variables in my data set to fit the regression model. Okay, so basically my data set is active new data set. So that's the data set after I renamed my variable names. After I did the dummy coding. And since I only want to use the training data to fit my model, so I specify the option subset equal to training.index. The training.index gives the index of the participants in my training data. So this basically means I will select this subset of data from the original data set, and then I will fit the regression model. Once I fit the model, I can take a look at the results of the model to use this summary function. So the summary regression dot model gives me the output look like this. Okay. There's a lot of information in the data set, but basically we can look at the regression coefficients. The estimates gives us the regression coefficient estimates based on this set of data. So now we have the intercept, the first row. So the intercept basically beta 0 is 0.122. And then we have the coefficients for all the predictors in our data set. So for x1, that's a grouping variable. We have 3 variables to recode our grouping variable. So therefore, we have 3 coefficients here. So those are the coefficients. Okay. And for x2, x3, x4, those are the coefficients. Okay. And in addition to the estimates, we also have the standard error estimates for each regression coefficient. So that's the column here. Using the parameter estimates and the standard error, we can calculate the t-value here. For example, let's take out the one value here, 1.172. So this basically equal to the estimates 0.043 divided by the standard error here, 0.037. The t-value here is 1.17. And based on the t-value, we can conduct the t-test to test whether this regression coefficient equal to 0 or not. For example, our null hypothesis here will be H0, beta 0, not beta 0 here. Here it should be beta 3 equal to 0. To do the hypothesis testing here, we can conduct the t-test. So we already know the t-value here. Based on the t-value, we can calculate the p-value. So this would be the p-value associated with the t-test. So the p-value here is 0.24. Clearly, it is larger than 0.05. And this basically means this coefficient is insignificant. It also means maybe there's no gender difference in the verbal test score after training. Similarly, we can take a look at the coefficient for x2, x3. For x2, based on the t-sets, it is significant, which means age would influence, age is related to verbal test score after training. So all of those interpretations is conditional on all other predictors. For example, if we look at the association between verbal test score and age, we assume the rest are the same. For example, they have the same gender, they have the same verbal test score before training. And for the coefficient of the verbal test score after training, it is also significant here. And if we are interested in knowing whether there's any difference in the training groups, is actually less straightforward. The reason is we have three coefficients here, right? So we want to look at the three coefficients together to see whether they are significant or not. Our null hypothesis here would be H0 beta 1 equal to beta 1 2 equal to beta 1 3 equal to 0. Right? So now this hypothesis testing of multiple regression coefficients together is not just a single regression coefficients like beta 3 and beta 4 here. How to do this test? In the regression framework, what we can do is we can actually conduct a model comparison, which means we can compare two models. One model is the regression model with x2 x3 only, x2, x3, and x4 only. And another model is actually x1 plus x2, x3, and x4. Here also I only use 1x1 here. We should understand it represents the 3 dummy coded variable. Okay. By comparing those two models, we can see whether this model, second model, works significantly better than the first model. If this model works better than this model, this means it is necessary to include x1. It is necessary to include the training grouping variable. Otherwise, we don't need to include that. So if it is significant, if there's a significant difference here, which means the verbal test scores are different for those 4 different training groups. So this is one way to test the significance of the grouping variable in the regression analysis. After we fit the 2 models, then I use the ANOVA function. What the ANOVA function does is it calculates the F statistic as well as associated p-value for the F statistic. So basically, ANOVA conducts a F test for comparing the 2 models. And if the F test is significant, here it is significant because the p-value is smaller than 0.05. So this basically means, okay, my model with the 4 predictors should be used. So this also means the grouping variable is significant. So for interpretation, this means there are differences among the 4 training groups in the verbal test score after training. Another thing we are often interested in regression analysis is the R-squared. R-squared can be directly found in the regression output. So that's a multiple R-squared here. It is 0.5078. This indicates that the variance in the outcome variable in the verbal test score can be explained 50% by the group of predictors. So in social science, R-squared equal to 0.5 is typically considered as a large effect size. Then based on regression, we can also make the prediction of the outcome. Doing the prediction means, okay, once we estimate the regression coefficients here, we can plug in the predictor values, and then we can calculate an outcome value, right, based on the set of predictors. For example, for one of them, for one participant, we can just use this to do the prediction. So the predicted value would be y hat typically we use equal to 0.122 times, here is negative value, so minus 0.16 times the value here. Maybe that's 1, right? And then x1, 2x1, 3, and then plus, again, minus 0.13 times age. Age may be 70 years old, so I plug in 70 years old. And then plus 0.04. Suppose this is female participant, so I multiply by 1. And then plus 0.64 times the verbal test score before training, suppose it's 20. Notice that by calculating this, we get a predicted value y hat. But in our original data set, we also observe the verbal test score after training. So which means we have one Y. So that's the observed value in the data set. Okay. And then we can also have the predicted value calculated from our regression model. So therefore, we can plot them in a scatter plot. So this is one participant. The observed value is about -4, but the predicted value is about 0. So those predicted value can be obtained using the predict function in R. So in this function, we have our regression model, and then we have our data set. Okay. We can do a prediction either using the training data or the test data. Here, I use the test data. In this case, my training data were used to estimate the regression coefficients here. Those coefficients. Then my test data was used to evaluate the performance of this model. So if the regression model works very well for this particular data set, we would expect, okay, most of those data points or most of those participants will fall closely on this line or very close to this line. So in this view, it means it's good. In the ideal case, every point should fall on this regression line. So that means we can predict the data exactly. But in practice, we don't have that kind of performance. Typically, there will be some like variations. We can quantify the performance of the prediction by calculating the difference between the predicted value and the observed value. Here, Y is the observed value, Y hat is the predicted value. This is the total squared error. The reason we square them is because the error could be negative or positive in the data analysis. So if we don't square them, the negative and positive value will cancel out. For this particular example, the total squared error is 150. This total squared error is related to the sample size. Typically, if you have a larger sample size,